Assalamu alaikum wa rahmatullah. Good morning, everyone. It's great to be here today. And the topic has advanced molecular technology in the title. And I think my task was to look at this figure, the cornerstone of how we do the initial workup in hematology patients, and see what are the advances, especially in the right side of the figure, in molecular study and cytogenetics. I wanted to bring some new technologies. I wanted to see if the current technology are being pushed so much that it will be very comprehensive or extremely fast or very cheap. And there is some interesting scenarios and findings that I want to share, 5 of them in fact, that's worth knowing today. So before I start, let me first of all understand with you what is the current situation today around the world. We wanted to see some of the leading oncology centers. This is a study published as a survey in 18 different institutes in the US, including the big ones, Mass General Hospital, Brigham, MD Anderson, and others. What they wanted to know is, what is the practice today? What is the challenges? And to give you an idea of how big is the load in each of these institutions, you will see the first 2 of them have 400 or more cases per month. Most of them, however, have 100 to 200 cases per month, and almost half have less than 100. So this is a diverse from small to very big institution. And this is an important figure because it will educate us how the high throughput affect our choices in the molecular labs and what technologies we can use efficiently. So the first question in that survey is, how big is your panel? Is it 50 genes? Is it more? You see that 22% have more than 300 genes in their panel. But the majority are under 150. And it's in 3 colors. Green color means it's a small panel that is focused on myeloid only or lymphoid only. The orange color is a combined bigger panel between myeloid and lymphoid. The red one is interesting. It's all cancer, solid tumor, hematology, everything in one large panel. And the thinking here is, maybe if we have only one panel, it would be much easier in the lab to do the work, which makes sense. But it also means bigger panels means more mutation that we don't know what to do with it, longer reports, more expensive. So understandably, it's only in 22%, while everyone else, or at least 2/3, have more focused panels. Another interesting question was how fast we can do, the NGS. There is superstars who can do it in less than a week, from 2 days to 7 days, from receiving the sample to reporting. However, more than half are actually between 1 week to under 2 weeks. And the final smaller group is within 3 weeks. And another question, they said, okay, so if you have acute stat case, what do you do? 50% of them says, 46% of them says we will use single gene assays. It's very quick, single PCR to do the results. And 40% before the last one say we'll use our NGS, the current one, but we will push it fast. A smaller group that is interesting, they say we have a smaller panel, the focused, very focused, but we will do it very fast. And I want to show you what does that mean, because it's very impressive if someone can do this in less than 5 days. One of those institutions is MD Anderson, where they developed a protocol, they call it ultra-rapid reporting of genomic targets, or shortly urgent-seq. And impressively, they have preliminary reports within 48 hours. It's very impressive. Look at the final report of the conventional protocol. It's within 4 to 5 days. So the conventional is already amazing, but they are pushing it to 48 hours in the preliminary report, and in the final report, it's less than 4 days. So what do they do? It's a multiple small adjustment in the whole workflow. It's not just the lab. In day 0, Any case that have blood received, it will be extracted. No question asked. It will be extracted and will be put ready for decision. Then they have a notification system that goes to oncologist, molecular pathologist, or hematopathologist. Any one of them flag it as a stat, it will go immediately into urgent seek protocol. That's day 0. The second thing that they do is they have NGS run every day. So it's not patched to the end of the week or in 2 weeks. Every day there is a run at 5 p.m. If the samples come early enough, it will be pushed in the protocol. And if it is coming in the early morning, it may go into day 1 NGS, which is very impressive. If it came late in the day, it will go on the next day. So they are ensured that within 24 hours, the samples has been extracted, flagged, and NGS has started. But there is more than just this. This is the workflow for the NGS from sample collection to reporting. And you will see that in the middle part is the sequencing, which is the longest part. It takes usually 30 hours to 36 hours. And they did something to reduce it to half. Basically, they went and said, let's look at how sequencing is being done. And normally, when we have DNA, we want to read from the end of it. We call it read 1, and the other end, which is read 2. So the red box is read 1, and the green box is read 2. And they say they hacked the system, basically. They really hacked it. They say, we will not wait until it's finished the sequencing. We want it to do only the first read, then we'll extract all the information, run the pipelines, and if there is a mutation, it will be reported. With this, they were able to shove almost 15 hours from the protocol. And they let the whole sequencing finish. That's fine, but that will go for the final report. They wanted to get as fast as possible to the raw data. And the result was very impressive. They only did 10 genes in RAS, NPM1, JAK2, and IDH1, and you see the mutation and how fast was the turnaround time. Most of them was in 2 days. And when they compared it to the conventional work that takes 4 or 5 days, the concordance was 100%. So whatever they picked up in the urgent protocol was the same as the full report. And this is a figure that I use to summarize what is the technology in different factors. How comprehensive is the list of biomarker content? How fast, turnaround time, and is it cost effective? And do we need a lot of capital expenditure, instruments, and hardware? And is it very sensitive for MRD? So this scores very high on the comprehensive biomarker content because we can go and cover almost everything. It can go very fast like what we saw, but I did not give it 5 points. The reason is this is really in 1 or 2 institutes in the world. You have to have a very good bioinformatics team. You have to have people who understand the technology itself. Usually, it's not as fast. I think the average is 7 days, 14 days at best, given there is failures, there is different experience levels, etc. So my subjective, this is just my opinion, if I would give it out of 5, it's 3.1 on average. But in the good hands, it can reach to 4 points plus, like we saw in the MD Anderson experience. The scariest things to us in the molecular lab when there is an update. And we heard today about WHO and Ellen recently. There is so many changes that how fast we can get this into practice. As you saw, there is different panels, and validating a panel takes up to 12 months or 18 months. So it's not a cheap or fast process. And back to those 18 institutions, they asked them how good or excellent your panel compared to the guidelines. And the answer was interesting. In the myeloid, 83% of them said we have an excellent coverage. What does excellent mean? Excellent means either we cover all the genes or we need only 5 genes to be added and to be perfect, which is great. 83% said we are at that level. 11% said we have a good coverage, meaning not everything is covered. Up to 20 genes can be missed and needed to be reflexed to something else. And 5% said we are poor coverage, meaning we are using a very generic panel that may or may not have the genes that we want. The story is different in the lymphoid. It's much less as excellent coverage in most of hospitals. Only 40% says they are confident with having a good panel, while it's much better in the myeloid. So one institution says, to solve this, I don't want to keep changing my panels. I don't want to change every year when there is a new gene, I have to do something else. So they wanted to see if they can combine the molecular and cytogenetics together. And there is two approaches so far for this. The first one is deep whole genome sequencing at 60x coverage, which basically means they wanted to sequence every base in the whole genome from end to end, whether it's genes or junk DNA or introns, everything. And this is, as you can imagine, is very expensive exercise. It can reach up to 8,000, 10,000 riyal per one patient, and a huge amount of data, almost 300 gigabytes for every patient, which means you need a big computational infrastructure. But they have done it, and this is a picture of showing a deletion at 13% cellularity, which is great. That means it is sensitive enough for low abundance biomarkers. In fact, it was so good that compared to cytogenetics and karyotype, they picked in the retrospective study all the recurrent translocation and copy number variants, all of it, 100%. Plus, they added the new findings in 17%, completely new, not picked by karyotype or FISH. And on top of that, they were able to optimize it to be finished within 5 days. And they changed the risk category for 16% of the patient. So this is extremely impressive. In fact, this is the largest, I think, technology that we have today in terms of how comprehensive it is. It takes 5 out of 5. But you can see it's not that great for MRD, so it cannot be used for that because it's only 60 coverage. And it is fast in Washington University, but I know for a fact that this is almost impossible for 99% of institutions because it requires so much bioinformatics and infrastructure to do it in 5 days. And it's not cost effective, of course, and require a lot of instrument. So it's very academic so far. Hopefully in the future we will see this more and more, but as of now, my subjective 5-star rating is 2.4 for us. So panels is way more practical, in my opinion, as of now. Another group have a different approach to this. They say, it's too expensive, let's do something different. We'll use a new technology. And the technology they used is called optical mapping. In theory, it's very simple. If you have a very long DNA as a spaghetti, can you move it in a small nano wells where you make it very long and strand, and then you take a picture. You are not sequencing, you're just taking a picture. And what you end up is having a very long DNA segments with these markers. You can think of this as karyotyping bands, basically, but at a very low resolution. And they map it, and the idea is very simple. If the space between this one and this one is expanding, then that means there is an insertion. If it's shrinking, that means it's deleted. If it is multiplied, that means there is copy number variant. So the technology is able to detect gain loss, deletion, and insertions, copy number changes, and impressively the balanced and the inversion as well. And the resolution is very impressive. At 500 base pairs, it has 95 sensitivity for heterozygous insertion and deletions, and even the larger one, balanced and unbalanced translocation, 50,000. For comparison, karyotype resolution is 5 million. Anything below 5 million cannot see. FISH is 100,000 base pairs. So this can go as low as 500. Very high resolution structure variant detection method. To simplify what does this technology means, you can think of it as combining karyotype, FISH, and microarrays in one protocol, which is beautiful because sometimes when you see something in the karyotype, you need to confirm by FISH, or sometimes you want to see it by microarrays. If you do it once, that's amazing. You have the 3 answers that you want from all the technologies. Early studies showed that in pediatric AML, that in comparison with karyotyping, they agreed on 6, which is this in the middle. The new technology detected 9 new structure variation, which is to be expected. It's very high resolution. It will see things karyotyping doesn't see. But the interesting thing that karyotype have picked 3 things missed by the optical mapping technology. So that is what I was interested to see. Was it a shortcoming of the OGM or not? These are the 3 cases. It says in the karyotype there is chromosome 11 monosomy. So they did FISH and they did the optical mapping. It was confirmed by FISH that it does not exist. So karyotyping was wrong in that case. Actually, it was wrong in 2 cases where it's confirmed by the FISH and was a false positive. So in theory, this is an extremely promising technology for the molecular cytogenetics and may enhance our resolution and novel discoveries of new biomarkers. My subjective evaluation for this is 2.8 as of today. I think in the next 5 years with more studies, this can go to 3.5, replacing a lot of tests in FISH and cytogenetics. The only issue is it's only structure variation. It does not detect DNA mutation. So you will always need NGS or single gene testing with it. The last 2 methods that I will go very quickly on is combination of FISH and flow cytometry. It's been around for 10 years, but recently it shows early studies or some stronger evidence for its value in the MRD. So it's a simple FISH, the one that we know all, but done with the flow cytometry. The impressive thing is it's increased the MRD detection level 10-fold compared to FISH, to the minus of 5, which is very impressive. And it is one of the most sensitive methods that we have today for MRD. But everything else is the same as flow cytometry, the shortcoming and the advantages. I think one of the major limitations is it is targeted. So you cannot do a lot of biomarkers at once. It needs to be selected, or at best 5 or 6 combination at one time. The last technology that I want to discuss is this. If you have seen some of these sequencers, it's a USB connected to a laptop. It does NGS for you very cheaply. And a group have used this in combination with the CRISPR, which we know all for gene editing. They use CRISPR to pick fusions and then sequence it. And the idea here is you don't need a PCR. And they were able to detect very important fusion in RUNX, BCR-ABL, BMR-RARA, at a very low cost, almost $80. That is very unheard of. This is the level of BCR. And the result, impressively, was done in less than 8 hours. In fact, some of the cases was finished in 3 hours. And I did not see any technology before that actually so fast, so cheap, with almost no requirements for a sophisticated molecular lab. The only disadvantage is it will not be used for MRD. It's not that sensitive. And you need only few biomarkers. You cannot sequence larger number. So this is very promising. Today, my subjective analysis is 3.6, which is amazing for a new technology. I think with the advancement, it can go for 4 or more stars. So 5 technologies. You see, none of them is actually solving everything. different patterns. Some are very good for MRD, some are very comprehensive, some are very cheap, but none of them is actually the perfect method today. But the incremental advances in these technologies is impressive. And this talk, I have to mention AI. It's a hype word. We really need to acknowledge that it is coming our way. I did not and will not discuss the impressive work that is being done in image analysis and combination with the genetics data into improving and automated reporting, including the karyotype banding. There is a lot of strong evidence that it will take the karyotype images, it will do the banding for us. Sorry?
2 minutes on.
Yes, it's the last slide. And I believe it's going to be the future, as we all have that hunch. It's not going to replace the practitioner, but it's an incremental addition. And it's coming our way, and we should embrace it slowly, because there is so much will change in our practice on a daily basis. And the final thing I want to bring your attention to is I'm humbled and privileged to lead recently a new institute called Applied Genomics Technology at KAXT with 2 goals. This institution is a national genomic lab, meaning it will be open for providing its infrastructure for researchers around the country. And we, as in Applied Genome Technology, going to be leading some of the translational of these cutting-edge technologies from basic science to clinical. So if you are interested in any of what I just described, please scan this barcode. It will take you to a registration form to have your interest. We have a lot of funded programs, and definitely would love to hear from you and collaborate together, whether you are a consultant, resident, a fellow, or have an interest in these studies. It's very promising and exciting, and I would love to start working with all of you on this. And thank you so much for listening.